All right, class, I think we're gonna get started. We just a touch early, but we have videos as well as some lecture to get through today. So I think I figured out what's going on. Just required actually restarting the computer was the problem. All right, so again, we talked a little bit about non-Newtonian fluids last class. In particular, shear thickening and shear thinning fluids. We'll look at some examples of each of those, as well as what are called viscoelastic fluids, which are even more strange than these shear thickening or shear thinning fluids. And so we'll start with non-Newtonian fluid. This is oobleck. So remember, a mixture of cornstarch and water being pressed through holes in a hydraulic press.
When the test is against non-Newtonian fluid, which is same as other. And as you can see, it's hard when you treat it, but liquid when you move it forward. So it's interesting to see how well it goes through these holes when we press it with full speed. And then we have also lots of more cool stuff today that are also requested by our viewers. So thanks for all the recommendations. Yes, so as I say, I get to go full speed and see how well it goes. And we are going to use 150 bars, and that's the limit what our tool can take anymore with my penalty choice. And here we go.
All right. You've already seen this video without audio, but the audio is basically why we show this. Sorry for language.
Well, you guys can be real fun.
So you can see what happened there, right? So we said that the shear thickening behavior of oobleck arises because it's a slurry of cornstarch in water. And when you, for example, hit it kind of hard or cause a large shear stress, then you actually start expelling the water from between those cornstarch granules, and they rub up against one another, giving rise to a fluid that behaves as if it's a little bit thicker. And here, we've actually pressed the liquid water out a bit, right? So it's really changing the density of this material, and ended up with something that's kind of like dry, basically cornstarch, worms, right, at the end. So this is the, this one's kind of fun. So again, this is a pool of oobleck, and we're going to watch what happens when you try to run across it. The quality of this one is really pretty poor, but it's kind of fun. Right, so as soon as it stops moving, the shear stress becomes lower, the fluid becomes less viscous, and he sinks, right? So we have someone sitting in the pool floating, and someone else running on top of the same fluid. So I think this is the best way to figure it. Simultaneously, the fluid is behaving as very inviscid, right? Very much like water, so floating inside, and also very viscous enough if to jump his way across. So one One way to analyze this is when you get to like a grad level, thinking about and start studying non-returning fluids, as you consider grad school, or in research. At some point, you might, like a more formal way of discussing this is to talk about the frequency dependence. So we'll talk about the frequency. So we look at how the frequency of the applied stress controls the effective viscosity of the material. So one nice visualization of that is to put some on a speaker and play different sounds. So this is from the slow-mo guys, so some slow-mo video of again, Oobleck. See, it's flowing right onto the speaker. And now it's jumping around almost like a solid, like flowing bit on top. And then it settles back out, right? As you turn off the speaker, it settles back out again when the high shear state is removed, right? It starts flowing again, just like a liquid. So these are all Oobleck examples of a shear thickening material, right? We also talked about shear thinning materials, one of which would be like shampoo. And so this is going to be an explanation of something called the K effect, which are these weird liquid jets that can arise in that kind of material. So we'll watch this.
I have this very, and I reproduced it here under what tends to be called laboratory conditions.
Right, so it has a stream of the fluid coming down, striking this kind of piled up material. Maybe your first hint that things are not so ordinary. And then we have this jet being ejected right from that stream.
Chaotic jets of shampoo firing in all different directions, appearing and disappearing. You're watching it in slow motion, by the way. This is about a fifth of normal speed. I now know it's called K effect, K-A-Y-E, and it's a result of the fact that shampoo is shear thinning, which means that it's viscous, it's thick, but its viscosity goes down under shear force. So the shear force is like this. You've got two things fighting against each other. Shear force in the case of a liquid is like if you've got a body of liquid and the top is traveling this way, at the bottom traveling this way, then you've got a gradient of velocity through the liquid. A shear force like that. And when you're applying shear force to the shampoo, it goes down. So why don't we do the jets again? Well, at the base, you've got this bed of shampoo, this viscous, and incoming, we've got the jets of shampoo that's also viscous. But because the shampoo piles up on the tray, occasionally you'll have the incoming jet hit the bed of shampoo at an angle. And when it does that, it slides along. And that sliding is a shear force. You have a shear force then. So in the boundary between the jet that's incoming and the bed, you have a thinning of the shampoo because it goes down. And it creates a layer of lubrication. So the jet is able to continue sliding further than it otherwise would. But because you've got this jet coming in with a decent amount of force, that actually pushes down and creates a dip in the bed of shampoo. So now you've got a jet coming in like this, and then it loops out, and it has a wound that it fires off. And
is firing back in on itself and it's killing the incoming jet, which is why it's chaotic, which is why the jets come and go. So why?
Okay, so I think that was kind of a cool explanation with reference to shear thinning. So so ordinarily, like for shear thinning, we're thinking about things like paint, right? We want it to stay on the wall, so we want it to be thick when we put it on the wall, thin when we spread it out. But this is kind of an interesting behavior. He has also a nice explanation of this, which I alluded to last time, about how we can think about what's going on at the molecular level that it gives rise to this shear thinning behavior.
How do you how they shear? Well, then couples, which means they're really long chain molecules. They're like these chains of beams here. And normally they're all tangled up with each other. They can't move very easily. And so they add viscosity, they add thickness. But if you apply a shear force like this, the molecules spread out, they smear out, and they line up. But then like that, they can more easily flow over each other. So this goes down, their shear thin. There's still a part of the explanation, because
Okay, so we're going to leave it there for now. Again, I give you links to all of these videos, including where we started them, in the slides, and I have the pages up on the Canvas page as well, so you can view them from there. With embedded videos, so it's a little bit easier to view. But if you want to go in and continue watching any of these that we don't have time to watch all of, those are available for you. So what we've seen so far are examples of shear thickening and shear thinning fluid behavior. But so far we've been discussing fluids as having, and we have just a few more videos to go. So far we've been discussing fluids as having as being purely viscous, as in having no elastic component of their response. So remember, so solids, when we apply a shear force, we see that they will eventually move. They resist that shearing that we apply to them. And you can think of that, and that is caused by the solid's elasticity, basically how spring-like the solid is. Newtonian fluids and the non-Newtonian fluids that we've discussed so far, shear thickening and shear thinning, are what we call pure fluids, meaning that there is no elastic component of their response. They never spring back. But there's a whole class of materials called viscoelastic materials that combine the viscous response to force, like a fluid, and the elastic response to force, like a solid. So this gets a little bit beyond the scope of the class, so we're just going to look at a few videos, and that's really as far as we're going to go. There's a whole world out there of things that are really neither purely fluid nor purely solid, and they give rise to all kinds of interesting different behaviors. So we're going to look at some examples of that in the next two videos. And so this one is really quick. We'll actually watch the whole one for you. But one thing I want you to ask yourself, and I'll stop periodically so we can discuss, is try to think of like, what would water do in this situation? Okay, just try to remember, or think about what water would do in the different flows that we're going to see in this video. Called the Barris effect, what we're going to see first. So before we start, we have some fluid, something like a shampoo, or so shampoo is actually more like a viscoelastic material than a purely viscous shear thinning material. But so we have this, we have some fluid sitting in a syringe, and we're about to advance the syringe and push the fluid out. So with water, what we would typically see, the water would come out, and as it would start falling, and as it falls, it will accelerate. And as it accelerates by mass conservation, we'll get into this when we discuss mass conservation. As the fluid speeds up, the fluid stream will get narrower and narrower, eventually break off the problems. But let's see what happens with a viscoelastic material. It bulges out. Anyone want to guess why that is? Why would it bulge out? This is a weird one.
Slow down.
Slowing down when it goes out. I mean, the fact that it's holding out tells us it has to be slowing down actually by mass conservation. The basic idea, and we'll get into a lot more of the math here, but if there's like some amount of material flowing through this cross-sectional area and going down, then if I go to an area that is smaller, in order to have the same amount of material going through per unit time, then it has to be moving faster here to conserve mass. And so if it's wider, then it means it's going slower. So definitely, yes, it has to be going slower here. But why would it bulge outwards? I mean, water doesn't bulge outwards. A pure viscous fluid doesn't bulge outwards. Any guesses? This one's kind of interesting. Yeah.
Is the fluid compressible? So it's being compressed at that.
So is it compressible? So it is an effect of the compression. The density is probably remaining about the same. But this is an effect of the compression, because if you notice, we're starting from a pretty wide area of the syringe, and then we're necking it down, and that's actually key. So what we can think of as happening here is this fluid is behaving a little bit like a solid. So it has elastic component of its response. So we start out with the fluid being in this like nice wide region, and then we squeeze it in, right, to pass through this narrow neck. Now, for a pure fluid, it doesn't care that you're squeezing it in. There's no elastic stress. There's no bounce back. There's no spring. But with a fluid that's behaving a little bit like a solid, it bounces back, right? And that's what we're seeing here. It's bouncing back, right? Springing back outwards and causing this kind of weird effect. That's one viscoelastic effect. The Weissenberg effect. So this is okay. So the setup here, we have a container full of the fluid. We're going to take this rod and spin it. Okay. So now in water, what happens when I spin the rod? What happens to the surface in particular of the fluid? Surface goes, so the whole thing spins. Surface actually goes down a little bit. So if you have something spinning really fast in viscous pure fluid like water, the surface of the material actually decreases as you move in towards the rod. But let's see what happens with this with this viscoelastic material. Climbs the rod, right? That's crazy. We'll see another video and explanation of that in the next one. And the third one is K effect. So we've actually seen this already. So this has to do with the material being shear thinning, but there's a component of the elastic response as well, causing it to pile up on itself, which gives rise to this. Okay. All right, last video on viscoelastic material, on non-Newtonian materials in general. So this is again going to be about the Weissenberg effect. Starts with a really cool visualization. So it's basically like Elmer's glue that's been dyed. It's like slime.
Why does this happen? What is the Weisenberg effect? Besides just another effect named after some dude. I honestly, the friend who has to be like, you know, about what's going on.
So this is they call it slime. It flows like fluid. So if I hold it like this, it'll flow. But if I pull it suddenly, it even snaps. The fluid moving around, getting dragged along, and that's going to happen in even water. Yeah, but with this fluid, this material also has a unique property called viscoelasticity. Not only is this fluid viscous, but it will bounce back to its original position. That's not the case with all fluids. The elasticity of this fluid makes it want to come back to fluid. So I'm going to use this spring as a model for that. So as it turns,
The sound,
it wraps up this string with fluid and it's tightening as it goes. That creates a tension. When you have a tension that's pulling around, it actually creates an inward force that causes it to collapse. So think about what's going to happen when this cylinder of fluid starts to squeeze
effect is essentially the fluid squeezing itself up the rod. And I felt, what's it like spaghetti when you twirl it around a board, except spaghetti is not fluid. Until it's, you know.
Okay. Yeah, but we'll see a lot more videos from her, I think, through the semester as well. Okay, so the last video I wanted to show you, I put the little caption, little blurb I gave on the slide is that Newtonian fluids are cool too. So because now we're going to turn our attention back to Newtonian fluids for the duration of the class. So if you're interested in these behaviors, then maybe you need to grad school and study them. Or I mean, and these behaviors also come up in chemical processes, right? So you know, a great many. So for example, in the shampoo example, there was discussion of the polymer additives that are added to the shampoo in order to you know, cause it to become thicker, right? So it feels more luxurious as you're putting it on, and to give rise to this behavior. You know, there's a lot of science in that and a lot of engineering and how you actually, you know, put these things in, find the right polymers, mix it all together, and produce such things at scale. And so, you know, there are a large number of, you know, important products that need chemical engineers to help make them that are non-Newtonian, that involve non-Newtonian fluid behavior. But there's a lot of interesting things that even Newtonian fluids, humble Newtonian fluids do, and that'll be the subject of this course. So this is a video about surface tension, which we're going to talk a little bit more about today. Okay, so we're talking about surface tension here. Right, so this kind of thin film type behavior that occurs at the surface or at the interface between, for example, water and air. Caused by hydrogen bonding, right, between individual water molecules at that surface. And here we can see how this bug, the water strider, can actually use that to basically walk on top of the surface of just ordinary water. And we'll talk about how that can give rise to pressures, right, within a fluid as well. Okay, any questions before we move back to lecture? Back to ordinary life. Okay. All right. So, okay, so we saw quite a few videos on, I forgot what I did over here now. Okay. There we go. Okay, so we saw a few videos, and again, these are on the slides, but also I'll put them up on pages on a page on Canvas with embedded videos, so you can see them a little bit more easily. All right, rough transition from water strider and beautiful music to math, but we have some deriving to do. So in the previous derivation, we were looking at a fluid element as we shrunk it down to 0 to try to understand something about the different components of pressure, or basically whether there are different components of pressure, whether it acts differentially in X, Y, and Z directions. And we found from that derivation, the important result was that if we shrink our control volume down all the way to nothing, then at a single point, we have the same pressure exerted in X, Y, and Z. So pressure is a point property, a scalar field. Think of it like temperature, distinct from something like velocity, which has X, Y, and Z components. Pressure is just a scalar, right? So it just has one value at every point in space. Nonetheless, we said that pressure can vary, right? So even though it has one value at a given point in space, it doesn't necessarily have the same value at two different points in space, right? So we can have a pressure field just as we can have a temperature gradient, for example, in the room, right? It can be colder near the vents than it is further away from them, underneath the lights or something. Pressure also can vary in space, X, Y, and Z, and time, right? It can vary over time if we turn on or off the air conditioning vents or something. So we're going to ask, what is the force exerted on a fluid element by a variable pressure field? And so our setup is, again, some little fluid element this time. We've drawn it as a little tiny cube of size dx dy by dz. And now we're going to start by looking at the forces due to pressure in the x direction. Where we have at this side, on this face, we have pressure, some pressure P. Right? We drop the x, y, z subscript because they don't matter, right? It's a scalar field. But we have a gradient in pressure, in this case here written as dp dx. So if we look at, if we move over to this other face of the cube, right, the pressure here is higher than the pressure here, or different than the pressure here by this value dp dx times dx, right? The gradient in pressure with x times the distance of this cube. So we're going to do a force balance. So mechanics course, we're going to do a force balance to find the pressure force in the x direction. So we're going to say the force on this fluid element in the x direction is going to be the force on the left side in positive x. Right, remember, it's always inwards by convention. Force on the left side in positive x minus the force on the right side in negative x. So it's the pressure on the right side is P plus dp dx times dx times the area, dy dz, gives us the force on this face. With me? Okay. And notice that we have this P dy dz, P dy dz canceling out between both terms. And we end up with the net force on this fluid element is minus, there's that negative sign I was warning you about, dp dx times dx dy dz. Okay. So we end up with, if we have variable pressure field, right, if pressure is varying in space, in this case, we're looking at variation in x, it gives rise to a force, a net force on fluid elements in the x direction. So pressure acts inwards, we're going to see the sign again over and over and over again, that negative sign. So we can do the same thing in y and z. We're going to get very similar results. And so we could write out the vector components of the net pressure force on a fluid element as negative I dp dx, j dp dy, k dp dz. And if we have an element of finite size, it's multiplied by the volume, dx dy dz. We are generally going to look at the force per unit volume. So we're going to divide by the volume of the fluid element and use little f instead of big F for the pressure. That looks like this. So the pressure force per unit volume on a fluid element, negative I dp dx minus j dp dy minus k dp dz. Okay. We will often simplify this using the gradient operator. So the gradient operator, we define this grad thing as I ddx plus j ddy plus k dbc. We're going to see this pop up again and again in our differential equations of fluid mechanics. But then we can simplify this thing into this, right? The vector pressure, remember it has three components, is equal to minus, we'd say minus grad P. That's how we'd say this, right? Pressure force per unit volume is minus grad P. Okay. And again, there's a negative sign that arises because of our convention that pressure force acts inwards. That's basically where that came from. Yeah, I saw a question. So now if we shrink that volume, yeah, so if we shrink that volume down, right, so that's, you know, this thing becomes really small, there's still a net force per unit volume that's related to the gradient of pressure. So we're saying if the pressure varies in X, Y, or Z, that will create a net force at that point on the fluid. Yes. Is that what you're asking? Yeah. Yep. Okay, great. Any other questions? Get out of your way. Okay. Okay, so we're going to use this. We're going to start using this to solve problems. But first, we have to introduce the concept of surface tension mathematically, I guess. So we saw how it affects water striders' lives, I guess. But we're going to talk a little bit more about how to use this in problem solving. So the sticking of molecules to each other causes a surface tension, right? So we can think of it as hydrogen bonding, right, between water molecules at the surface as they line up on the surface, creates a small force, but nonetheless a force. And that force is parallel to the surface, right? Because we can think of that that orientation of the molecules being parallel, arranged along the surface itself. This Y or upsilon, sometimes read as capital upsilon, is the coefficient of surface tension. It has the dimensions of force per length, right? I haven't put that in primary dimensions, so force is, remember, a secondary. But force, right? Remember, we can find as what, mass times acceleration, and we could resolve that into primary dimensions. But it's useful to think of it as a force per unit length. The value of this coefficient of surface tension depends on the liquid and gas on either side of the interface. So it's not appropriate to talk about a surface tension for water. You have to think about a surface tension for water in air. Okay. So if we change the gas on the other side of that interface, we would also be changing the surface tension. Right. So if we put it in helium, right, if we had water in helium, we would have a different surface tension coefficient than if we had water in air. So this also depends, the surface tension coefficient depends a little bit on temperature and very greatly on contamination, right? So if you have something, even a very small amount of something within your fluid phase, for example, it can give rise to a vastly different surface tension, coefficient of surface tension. So soap, but even a tiny amount of soap can greatly disrupt the surface tension of, for example, a water-air interface. Okay. So most likely, if you somehow are dealing with surface tension, doing some experiments on it, and it's not going the way you expect it would go, it's probably not the temperature effects. It's probably some kind of contaminant that you have. But for water, the value of the surface tension coefficient, 0.073 newtons per meter. So again, it's pretty small, right? That water strider is pretty lightweight. You know, when you step into a puddle of water, you don't float on top of it because you weigh quite a bit more than that water strider. So this is a fairly small force. As I mentioned, this surface tension can give rise to a pressure when we have a curved surface. If we look here, imagine we have a droplet of water, right? A nice round droplet of water. What I'm saying is that if the interface is curved, the pressures on the outside and inside will not match. And so let's just think through what a force balance on this should look like. Okay. So we have, if we consider, I've taken like a little slice, a dark blue slice up top. I'm just going to cut through the top of this droplet, and we're going to do a force balance on that cut surface. So on the inside of the droplet, we have some pressure. And what direction is that pressure force on the cut surface of that droplet? What's the net direction of that pressure force? Up or down? I hear down. Anyone say up? So the element that I'm considering here, right, this is important. The element that I'm considering here is going to be just this dark blue one, right? So we're considering just this dark blue slice of the droplet as our fluid element. The pressure force, let's say the pressure from the inside, right? Pressure, remember, always acts inwards on a fluid element. So if pressure is acting inwards on this fluid element, it's acting up, right? On this little dark blue slice. See confusion. So remember, when we drew our fluid element that was sitting out in space, right? We had our cube, pressure was acting inwards in all directions, right? So from the outside fluid inwards to our fluid element. The same thing's happening here. I've just changed the geometry, right? So now we have this dark blue little cap of our droplet, and the pressure from the inside is acting upwards on this cut surface. Yeah.
It's like, I can imagine that droplet in air, when there wasn't air, there's pressure from the air.
There is, exactly, yes. So that's the other component of this that we're going to talk about, right? So first, so the pressure, so there's going to be an upwards force acting on this little cut surface from the fluid, from the rest of the fluid inside of the droplet. So it's the pressure inside acting upwards on this cut surface. There's also going to be a net pressure force from the, let's say this is water and air. There's going to be a net pressure force from outside that's acting downwards, right? So we're really everywhere normal to this sphere, but the force, the component of the force in X on either side would cancel out. So we're left with a net force that's exerted downwards on this little cut element from the pressure outside. Forget that. Who's confused on this? Yeah, go ahead. I want you to raise your hand. Yeah, just generally confused. Okay, great. Let's just draw it. Yeah. Yeah, the blue section is pushing down on the light blue inside. Yeah, that's correct. So if we have a droplet sitting here. And now we're just going to take a cut through the top surface of this drop. Okay, just at some random point within the drop. And now this is going to be our fluid element. It's going to be this little hemispherical cap of the fluid element. And now we're just doing a force balance on this little tiny piece of fluid, right? So we're no longer considering some arbitrary cube in space, considering this like rounded cap of the fluid drop. And I'm saying in this problem, there's a pressure in general inside of the droplet, of this droplet of water, and there's some pressure outside, right, like atmospheric pressure or something outside of the droplet. This pressure inside is exerting a force acting inwards on this fluid element. This pressure outside is also exerting a force acting inwards on the fluid element. Okay. I'm going to start, yep. No, because there's one more force to consider. Okay, so if there were no more forces, but if there were no more forces to consider, so if surface tension were 0, or if we were considering just some random, hemispherical cap, right? If we had water outside and water inside, then the pressure outside and inside, and the pressure outside and inside were equal, then these two pressures, then the net force of these two things would be the same. But we also have a surface tension, which is acting at the edges. Yes. If the pressure force on the outside and inside were different, it's going to be balanced by the surface tension. So if there were nothing balancing it, then yes, it would flatten out. But in this case, we also have a surface tension force caused by the molecules on the surface of this droplet binding to each other, holding tightly to each other, exerting a force per unit length to hold together to one another, right? They don't like being cut apart, for example. They're holding together like a skin on the surface of this droplet, right? Imagine almost like the elastic skin of a balloon, right? That's basically what we have at the surface of this droplet. It's just water, hydrogen bonding to itself. Yeah. So the pressure on, so the net result is if we have a, so from the outside, we have some pressure on the outside, which results in a net force acting down. Plus, right, if we think of the other component of the forces acting down is the Y component of the surface tension force, right? So that's the force acting down. That's balanced by the pressure on the inside. And the only way for that to be true is if the pressure on the inside is actually greater, right? So we have the pressure force on the outside plus the surface tension being counteracted by the pressure on the inside. Yeah. So so the surface tension is parallel to the surface. So when we cut it here, we end up with it being this force right here. Okay. So the pressure on the inside has to be higher. Yes. So it actually doesn't matter where you cut it. It's easiest to cut it along the hemisphere for this derivation, but you get the same result once you do all the trig and resolve all the areas and everything together. But you do get the same result. So just conceptually, so we're gonna show what that result is. Give me 1 second. We're gonna show what that result is. But just conceptually, I just want to get across that the pressure on the inside is higher than the pressure on the outside, and we'll look at the math of exactly what it is. Yeah, so if you look at this, we could divide this into a Y component and an X component, right? In this case, the X's are going to cancel each other out, right? Or we could do the easier thing and just cut it along the hemisphere, which is what we'll see in the result from your textbook. And then there is no X component to worry about. Okay, good question. Yeah. Any other questions? Yep.
Imagine some force on the inside of that element.
So we're saying this, so the X component is going to be balanced on both sides. So this fluid element is at rest. We're considering the fluid element to be at rest. There's no acceleration. So all the forces balance. To start with, we were just considering the force in the Y direction. And that tells us just conceptually, just that the inside pressure is higher than the outside pressure because of the effective surface tension. That's the main thing I want you to get from this. But if we consider the X components, they actually would all cancel. If you imagine this like skin, right, taut skin of the balloon of this water droplet, right, caused by surface tension. The X component going all the way around, right, is always of the same magnitude and pointed in all different directions, and so that cancels out. And the X component actually of all these pressures, right, exerting inwards as we move all the way around the whole surface, they actually cancel out as well. So the only case where we are really learning something is in the Y direction here. Yeah. Yeah, so in water, it's because of hydrogen bonding. Other intermolecular interactions give rise to surface tension in other fluids. Yeah. It's actually one of the reasons why it depends so strongly on the two fluids that you have and essentially their miscibility, right? So if you had two fluids that mix really well together, then you tend to have lower surface tension between them. Okay. So if we do this, and now we cut along, we take a cylinder of fluid, and we cut along the hemisphere of that cylinder. Imagine some infinite cylinder, and basically just apply a force balance, again, in this Y direction. The end result is that the pressure, the delta P, the increase in pressure inside of that cylindrical element is just this epsilon over R, where R is the radius of the radius and curvature of this cylinder. We can do the same for a sphere, right? So if we have a sphere, if we want to simplify our life for the derivation, we make a cut along the hemisphere. What we'll show is that, and what we would see is that the net force is going, or the net increase in pressure is going to be 2 epsilon over R. So the concept takeaway here, we have a curved surface with surface tension. It gives rise to an increase in pressure. We have positive surface tension, increase in pressure inside of that surface. Yes. Here, I would just expect you to be able to use this. Yep. So that's one concept, though, is that I do expect you to know is that the pressure on the inside of a droplet with surface tension is higher, right? And the second is that it depends upon the shape. Okay. So it depends on the shape. So cylinder, sphere, different. And in general, for some arbitrary curved surface, so we can think of at any point within some kind of a curved surface, you can think of there being two different radii of curvature, one in one direction and the other in the other direction, in a perpendicular direction. Call that R1 and R2. And so this delta P, we would write as epsilon times 1 over R1 plus 1 over R2. So if you're given, for example, the curvature of a surface, you can find the increase in pressure on the inside of that surface. Okay. So another, yes. Would anything change if the droplet were in a vacuum? Yeah, what might change if the droplet were in a vacuum? The atmospheric pressure would not be there. So the surface tension would also be different because now we'd have something different outside. We'd have a vacuum outside. I think in the end, your droplet would not be stable inside of a vacuum. Yeah, I'm trying to think. I mean, it would just turn to vapor and be pulled out by the vacuum. Yeah, it wouldn't exist inside. It wouldn't be able to exist inside the vacuum. Yeah. But in general, as we change, if we're changing the fluid outside, right, then we would also be changing the surface tension. And yes, the pressure outside would be changing as well. Yeah. But I'll think about that as well. That's a good question. Like, what happens if we just lower the pressure? Maybe we put it in a vacuum chamber, we don't take it all the way to vacuum. And there, I'm not sure. So I'll have to get back to you. Okay. So another what we call an interfacial phenomenon, or another property of the interfaces of fluids, is called surface wetting. So liquid in contact with the surface interacts with the surface as well. This gives rise to what we call the contact angle. So if we have a droplet of a liquid in gas phase sitting on a solid phase, right? So we have 3 phases here. Then there will be some angle at which, if we take this droplet contact line all the way down to that solid, there'll be some angle of that contact line that we can define, some angle theta. We call this the contact angle, and we say that if this angle theta is greater than 90 degrees, then it's non-wetting. So imagine, so this is greater than 90 degrees, this angle theta, and you can imagine getting even higher and higher and higher, means this thing in the center, this drop in the center, is getting more and more like a complete sphere, right? Think of the liquid as like pulling away from the solid because it doesn't want to wet that solid. That's like what happens with air, water, and wax, right? If you put that Rain-X stuff on your windshield before a rainstorm, you see all these nice little droplets beating up and rolling off. That's because you have a really high contact angle. If theta is less than 90 degrees, we define it as wetting. So for example, in glass, really clean glass, if you apply a drop of water, it spreads out. It's actually one way to tell how clean glass is. This depends on the gas, liquid, and solid. So surface tension depends on both the gas and the liquid, right? This depends on all 3. All right, and that's where we're gonna call it for today. Next time we're going to continue talking about this, about fluid statics. We're gonna talk about force due to gravity and how we can use that to find forces within a static fluid. Yes. Yep. 1 second. Stop share.